All right, chemistry grade 12s and 30s. We're going to just quickly look at the differences between the molar enthalpies of formation of a particular substance and that same substance's molar enthalpies of reaction, and basically what's the difference between the two. So to start off, it's really the reaction itself that we're talking about. When it comes to molar enthalpies of formation, remember that it's the energy released. Usually it's released. In some rare cases it could be absorbed, but it's energy released as a compound is formed from its elements. Okay, so it's specifically the elements that form the compound. So for example, let's say we have the substance C2H5OH, and we want to know the molar enthalpy of formation. It's not, a particular organic reaction that we're looking at that makes, ethanol over here. The molar enthalpy of formation of ethanol would be the energy that's released as carbon solid, hydrogen gas, and oxygen gas combine in order to make C2H5OH. And so, of course, having this reaction balanced, we put a 2 in front of the carbon, 3 in front of the hydrogen, and a half in front of the oxygen. And the thing is that this has to be per 1 mole, right? So we'd have to balance everything accordingly so that you end up with just 1 mole of the compound. The other thing to remember is that it's a molar enthalpy. And so that's in kJ per mole. And the symbol that we give the enthalpies of formation is delta H subscript F for formation, and this degree symbol just means under standard conditions. Now, the enthalpies of reaction are really any compound that is involved in a chemical reaction, and it's not necessarily formed from its elements. So if I take C2H5, for example, and so remember, this is the energy released or absorbed per mole of a compound in a reaction. It could be in a reaction. So let's say I take ethanol over here. Now, one way that we can make ethanol is through a hydrolysis addition reaction of an alkene. So we can go C2H4 gas plus H2O. Okay, and this could be liquid or gas. Would give us C2H5OH. Now here we have the same compound, ethanol, but it's not formed directly from just combining the carbon, hydrogen, and oxygen. It's combined by other compounds in the reaction. And so the energy released making the compound this way versus making it this way would be different because you're combining different things. Now, if we go to pages 4 and 5 of the Chem 30 data booklet that you can find on the website in Alberta here, we have a bunch of standard molar enthalpies of formation for various compounds. On this table, we have the compound names. So if we look, for example, aluminum oxide over here, we have the compound formula, the state as well, because forming aluminum oxide solid is different than forming it as a liquid. And we have the enthalpy change per mole, which would be negative 1675.7. The overwhelming majority of these have negative molar enthalpies of formation values, and that's because in the majority of compound formations, energy is going to be released because making bonds releases energy and breaking bonds absorbs energy or requires energy to do that. And so we can then take these enthalpies of formation, which are the enthalpies formed exclusively by the combination of pure elements to make compounds, and we can plug these into the reaction. So as I said, if it's closed, H2O liquid is produced, and if it's open, H2O gas is produced. The second thing that we're going to want here is a balanced combustion reaction, because we're going to use those coefficients to help us calculate the enthalpy change using molar enthalpy change of formation. Next, we're going to use the enthalpy change equation right over here and substitute the delta H products minus delta H reactants with our chemical equation, and it should look like this. So we subbed in our products and our reactants. Here's the sum of the products minus the sum of the reactants. And one thing I'm going to write here before we start plugging in the numbers is that if you look at O2, this is not a compound. And so pure elements, when it comes to the enthalpies of formation, because they don't form compounds, and the enthalpy of formation literally is defined as the amount of energy is released or its subcases absorbed as a compound is made from its pure elements. If it's not a compound, then it won't have a molar enthalpy formation. So we're going to write pure elements are always 0. And so all I'm going to do here is just cross out the oxygen here and put 0. And it doesn't matter whether it's oxygen, fluorine, chlorine, etc. A pure element is always 0. Now all we're going to do is go to our data booklet and insert, wherever we've written the compound here, we're going to insert the molar enthalpies of formation. Now our molar enthalpies of formation values for all the compounds that we're going to use in Chem 30 can be found on page 4 and 5 of the data booklet here. So if you look, it's listed in alphabetical order, and all we have to do is, for example, in our equation we want butane. We look at butane over here, and then we can see that it's negative 125.7 kilojoules per mole, and as well the likes of carbon dioxide over here, CO2, at negative 393.5. And then, of course, since we want water liquid, not water vapor, we're going to use the water liquid value of negative 285.8. And so we insert these into the equation as follows. So you plugged in all of these values. Now remember that the coefficients in the balanced chemical equation represent the number of moles of that compound, right? Or the mole ratio. And so all the mole values would cancel out. We would plug this into our calculator and we would get the following value. And so plugging in those values, we would get finally a grand total of negative 5,754.6 kilojoules. That would be the enthalpy change of reaction. And if I were to plug this in to scientific notation, if I wanted 3 digits, and the diploma is going to specify how many digits they want, we can put this in the scientific notation, which means we just move the decimal spot over to the 5, and that becomes negative 5.75 times 10 to the 3 kilojoules. So now using the data booklet on pages 4 and 5 for all the available compounds in this reaction, I want you to determine the enthalpy of reaction for 4 moles of ammonia gas plus 7 moles of oxygen gas, which yields to 4 moles of nitrogen dioxide and 6 moles of water liquid. So again, using the molar enthalpies of formation, I want you to calculate the delta H value for this reaction. So pause the video, and then when you're done, unpause it and see if you got it right. So hopefully by now you've had a chance to find or locate the molar enthalpies of formation of all these compounds, and you would have plugged it in as follows. If you look at the highlighted portion in yellow here, that's just me canceling out the pure element, because pure elements always have a molar enthalpy of formation of 0 because they're not compounds, or they're not forming compounds. So we plug it all in, and when we place brackets in our calculator carefully, we should get a value of negative 1397 kilojoules in total, which is quite an exothermic reaction. If you're not getting these values, but you find that you're doing all the rest of the plugins correctly over here, then just check the brackets of your calculator. All right, so that's the simplistic introduction to molar enthalpies of formation and an alternative way of calculating your enthalpy change of reaction. If you're looking for more complex problems, then the next video will give you that.